All right, let's go ahead and continue on with a lecture, another one on substitution, but this time we're going to be talking about it in the context of definite integrals as opposed to indefinite integrals. And if you happen to have seen this phrase before, the fundamental theorem of calculus, that's what we're going to be talking about today. I won't officially state this definition or exactly what this theorem is until a bit into the lecture, but let's go ahead and get started. And we're actually going to start off with an example that looks very similar to another example that we've already done before. So we've seen an example of an integral before where we had 2x plus 5 to the 7th dx. And we saw that this wasn't some simple application of the power rule. We actually had to worry about this substitution that was involved here. So we had to go along. We had to set u equal to 2x plus 5, and that was going to lead to du is equal to 2 dx, and then we moved on and we finished out that integral. Well, in this case here, what you'll notice is it's the same integrand, but I have limits of integration now. And so what I want to talk about here first is what happens to these limits of integration when I do my substitution. So let's go ahead and give ourselves a new slide here, and let's put this definite integral right here. All right, so we've got that right there. And as we might expect, we've done this before. U is equal to 2x plus 5 du is then going to be 2 dx. And then if we want to, for good measure, we can go ahead and solve this for dx. And then what we might expect to do is just go ahead and put, okay, 2, 5, and then let's substitute our 1/2 du in there, and then we have a u to the 7th. And this looks all fine and dandy, but there is in fact a problem with this. If we were to continue on, the issue is these limits of integration. As this integral was written in the get-go, it's not explicitly stated, but it should be understood that 2 and 5 correspond to x values. We've seen that as we've talked about definite integrals, as we've talked about Riemann sums. We've seen that this 2 and 5, they correspond to a graph of this function. In this case, we're dealing with just a nice polynomial here. So just to be general, I don't know exactly what this polynomial looks like, but we're just looking in between 2 and 5 here, and we're looking at the area underneath that. So we'll be looking at this green area all in there. And so we should be able to understand, even though it's not explicitly written here, that this 2 and 5 are in fact x coordinates. And as we've emphasized when we do substitution, we emphasize this when we did it on indefinite integrals, but it still applies here. We want to make sure that we have our entire integral written in terms of u. You don't want to have any x's lying around. If you have an x lying around, that's bad. We want to make sure that we're converting our integral from a function of x all the way to u. And the problem here is that what we've got is we've got x equals 2 and x equals 5 still in there. And you'll notice what I'm adding in here in the green. I am a big fan of doing this personally on a lot of my integrals. For me, when I'm doing more complicated integrals, or if I'm showing it, if I'm doing an integral for someone else, I really like to explicitly write x equals next to my limits of integration, just to really emphasize that, hey, these are in fact x values. They don't look like it because they're just numbers, but they are in fact x coordinates. They are x values, as we can see based on the graph and understanding what an integral actually represents. And so this right here is a problem as it's written, because it's not all in terms of u, it's in terms of x. Before I explain how to sort of fix this, I do want to mention that this in the green, this addition of x equals, that's not very common. I do it a lot, but and other mathematicians do it as well. It's not super common though. It's not something that you'll see all the time. but I'll do it every once in a while. So just wanted to point that out there. All right, so as we've seen before, whenever we don't have all of everything in U, we gotta figure out a way. We have to get clever with it and turn things into U. And so luckily, since these are in terms of X, I actually have a formula that relates X and U. So what I'm going to go ahead and do here, first things first, let's go ahead and erase those endpoints because we want to change those actually to U endpoints. So I have a function U equals 2x plus 5, and that is a relationship between U and X. So as I've said before, what we can do, and you by no means have to do this, but you can write this explicitly in function notation, U of X equals 2x plus 5. And I mentioned that before solely for this purpose now on this exact example, because now it's very easy to see that we can continue on here and we could evaluate U of 2. So right there, I'm plugging in X equals 2. And when I do that, I end up with 9. And then I could also plug in U of 5. And when I do that, I get 2 times 5 plus 5, which is going to give me 15 right there. And so right there, what we've done is we've actually converted our limits of integration from X and converted them into U. And so I can just do that here as well on that integral. Again, you don't have to write the U equals, but I am going to just to be explicit. If you don't want to, your integral would look like this: 9 to 15, 1/2 U to the 7th du. And this right here is an integral that is completely in terms of U, and you can go on solving it with a simple power rule application, just like you normally would, and you can move on and you can actually evaluate and get that number out. Let's go ahead and do that actually, just for practice here. So we'll copy this over. So this is where we were at so far. We'll go ahead and write out the starting step here. So we had 2 to 5 of 2x plus 5 to the 7th dx equals all that right there. So there's obviously a lot in here, but in this equal sign, but we did that on the last slide. So let's go ahead and continue on here. We're going to do our simple power rule. So we're going to add 1 to that exponent, and we are going to divide by that resulting exponent. So when I divide by an 8, that 1/2 becomes a 1/16. And then remember, because we have a definite integral, we want to make sure that we're actually evaluating at 15 and 9. And again, this is actually a point where I like writing U equals right in here, kind of squeeze that in. You don't have to. I do it every once in a while, but in this case, we understand that these are U endpoints here. So we go ahead, we have 1/16. And you notice a little shortcut that I do here. I'm just going to keep that 1/16 factored out because we know that it's going to be distributed to both. We know that it's on both of them, so I can just leave that factored out, and that's totally fine. And so in this case, maybe you have a calculator on you, maybe you don't. You could evaluate 15 to the 8th and 9 to the 8th and actually do all this. I'm going to go ahead and just box this as an answer. We don't know. I don't have a calculator right on me here, but that's fine. This is an acceptable answer. And there we go. We get our answer right there. And you'll notice once we moved away from X's into U's, we didn't ever go back because this is a definite integral. We just get a number and that's our final answer and we're done. So there was no reason to go back into X's or anything like that. What I do want to mention is that some other places will actually teach this concept a little bit differently. Some textbooks, some places online, they actually won't change these to U's. They'll leave them in terms of X's. And then what they do is once they get to this step here, they actually convert this U back into X's. And it works, and it technically is fine. I mean, it gets you the same answer. I'm not a fan of it for a handful of reasons. Two primarily. One, and this is probably the more important reason. One is that this statement that I'm about to write here is not correct mathematically. If I write this statement here in the red, obviously there's u sub that's going on in here, right? We have our u equals 2x plus 5, and our du equals 2 dx in there. But this statement here in the red, this is not mathematically correct, because it's assumed when you're writing an integral out that these limits are given by that variable of integration. So here, if I just sort of covered all this up right here, and I just wrote this integral, you're going to assume that the 2 and 5 are in terms of u, because why would you assume that they're anything else? The u is stated very clearly as that variable of integration. So this in the red is an incorrect mathematical equation. Now, if I wrote this, that technically would be correct, but it's also just confusing because I'm mixing x's and u's, and it's just weird. So really my big reason why I'm not a fan of waiting to convert this u back into x's is because this first statement here is mathematically incorrect. The other reason I'm not a fan of it is that if you're going to do a u sub, why not change everything all at once? I mean, you're already doing the work of changing the 2x plus 5, the dx. Why change everything to u's, do an integral, and then go back into x's? You might as well just go ahead and change all of your x's into u's in one fell swoop, get it all over and done with, and then it'll actually save you a lot of algebra once you get here and you actually evaluate the integral. It'll be a bit easier. So if you happen to stumble upon other sources for this fundamental theorem of calculus and you see people not changing their bounds and instead taking this step right here and rewriting the u in terms of x's, it technically works, but I am personally not a big fan of it. I've found that students that do that tend to miss these problems more often than students that do it my way / this way / probably the more common way, actually, and the more mathematically appropriate way. All right, so we've got all that. We've seen this. Let's skip over this. We did all that. Keep going. So this is the fundamental theorem of calculus, this whole idea, everything that we just did in that example. This is what we call the fundamental theorem of calculus. And basically what we looked at it was in the context of substitution, but it doesn't matter what integral you're doing. If you're doing an integral that requires substitution, if you're doing a very simple integral, if I just gave you an integral that looked like integral of 2x dx from 1 to 3. That integral, the fundamental theorem of calculus still applies to it. And all that it says is that if I take this definite integral, when I actually evaluate the integral, I then just have to evaluate at b and a. And we do that by just subtracting those two differences there. And we've already seen this. We've seen this before. We've looked at this. I just didn't give it the name fundamental theorem of calculus. Really kind of the point being that I didn't want to really confuse ourselves with this big, seemingly named theorem. I just kind of wanted to introduce it, in the, sort of in the middle of the, integral lectures, and just kind of take it as it came, and not worry about giving a big old theorem name to it. But there is a big theorem name to it. It's the fundamental theorem of calculus. We've done it already. Don't let that name scare you. We obviously have some of these little conditions, like f has to be continuous in between this interval. We don't want f to be, discontinuous. That would be bad. That would be hard to take an integral of a function that was discontinuous. So we've got that. This is the fundamental theorem of calculus. One other thing I want to mention, if you caught on the last slide that it said fundamental theorem of calculus part 1, there's actually other parts to the fundamental theorem of calculus. And this is what we just did. It mentions changing the limits of integration from X to U. And that's the example that we just worked out. And so fundamental theorem of calculus, all wrapped up in this idea of definite integrals and how we do them. We've dealt with it before, just assigning a name to it now. So let's go ahead and do another example. And this time we'll be looking at an integral from 0 to e of ln of 5x plus 1 cubed all over 5x plus 1 dx. And what I want to try and emphasize here in this example is actually how similar it is to a problem where maybe I take away those limits of integration. There's really not a whole lot of extra work that has to be done there. So let's go ahead and start off. We clearly are going to need to do a u sub here, and I have options here. I could try doing 5x plus 1, and then du might be 5 dx. And if I did that, I'll end up, I still have to change these, but as we're going to see, this doesn't work, so I won't bother changing those yet. U cubed, oh, excuse me, we'd have ln of u cubed over u. And to me, that doesn't seem like a very simple integral. And so this u sub of 5x plus 1 isn't going to really make things that much simpler. So let's try something different than 5x plus 1. That's a great example of that work right there of, hey, we tried it. It didn't really do anything. It didn't simplify things. Let's just go back, erase our work, and try something else. And I'm going to try ln of 5x plus 1. And here we got to actually get out sort of our derivative thinking caps, and we got to think about how we actually take this derivative. So when I see an ln, I definitely have a 1 over whatever's on the inside. And then chain rule says that I have to multiply by what's on the inside, by the derivative of what's on the inside. So the derivative of 5x plus 1 is just going to be a nice simple 5. And then don't forget our dx here. So when I'm looking at this du, I notice that right there, I have a dx over 5x plus 1 and a dx over 5x plus 1. So what I like doing is I like dividing both sides by 5 here. And now I have 1 over 5x plus 1 dx. And this is great. We've got all that. I'll have my integral, and then I'll have u cubed right there. And then that dx over 5x plus 1 is just 1/5 du. Let's make that look a little cleaner. And then just tidying that up, let's pull the 1/5 out. You'll notice that I'm leaving off those limits. For now, I'm going to go back and do that. So we got that. So we're still not done, obviously, though. We have to do our limits of integration. So let's go ahead and write u of 0 is ln of 5 times 0 plus 1, which is ln of 1, which is 0. And u of e is ln of 5e plus 1. That's actually that right there. There's not really much more simplification that we can do on that ln of 5e plus 1. I'm going to go ahead and change the color here just to make that look a little better. And so our limits of integration are going to be 0 and ln of 5e plus 1. While that does look kind of ugly, that's what it is. So we just got to leave it like that. So let's go ahead. Let's do this integral. So we have a u cubed. Very simple power rule is going to say 1/5 times 1/4 u to the 4th. So I'm going to add 1 to that exponent and then divide it by the resulting power. Let's make that, let's clean that up a little bit. So ln of 5e plus 1, and then we are actually still going to have a 0 there. Awesome. So now if we simplify just a little bit, 1 over 20 u to the 4th of ln of 5e plus 1 and 0. So 1/20th times ln of 5e plus 1 to the 4th. And you'll notice here that this is just going to be minus 0, because if we plug in 0 right into u, then that just is 0 to the 4th. It just goes away. So I'm just not going to bother writing that there. And we've got our answer. Boom, right there. Wonderful. Let's go ahead and do one more example here. So we're going to look at the integral from 0 to square root of e of x over x squared plus 2 dx. And again, we're going to see this similar idea. Let's try setting x squared plus 2 for u. du is going to be 2x dx. And I see an x dx up there, so I like to just divide that 2 over. It's not necessary, you don't have to, but I like writing that out because now I can very easily see that x dx right there, that they match up. So continuing on, u of 0 is going to be 0 squared plus 2, which is just going to be 2. U of square root of e is going to be square root of e squared plus 2, which is just going to be e plus 2. So we'll go ahead and we'll convert this integral into u now. So I'll have 2 to e plus 2. And then remember that x dx was a 1/2 du. And then that x squared plus 2 on the bottom is a 1 over u. So I can clean this up a little bit. 2 to e plus 2 of, let's make that a little bit better. Got 1/2, and I have a 1 over u du. When we integrate 1 over u, we get natural log of the absolute value of u. Don't forget that absolute value. And then we're evaluating at e plus 2 and 2. So then we'll go ahead and we'll just plug things in. Let's give myself a little bit more space. ln of e plus 2 minus, again, another 1/2. And actually, let's, well, yeah, we'll just write 1/2. ln of the absolute value of 2. We can actually simplify this quite a bit. I can factor out a 1/2. And I have ln of e plus 2 minus ln of absolute value of 2. You could actually even simplify this one once more. You could recognize that these natural logs are subtracted by each other, so I can actually bring them in as a division. And that right there is about as simple as you could make it. You could even do one more step. You could take this 1/2, you could bring it up top as a square root of all that. It's not necessary, but that's something that we might want to do. You will notice as well that e plus 2 divided by 2 is positive. So this in here is positive. So these absolute value signs are not necessary. But as I've mentioned before with natural log integrals, while they may not be necessary, they don't hurt. You can put parentheses and it's still correct. But having these absolute values is fine. So I always like leaving them there just to be very explicit, just in case whatever's in here ends up being negative. So that's going to be our example there. Hopefully you can notice that this isn't really that much different than doing a regular substitution integral. We just have this extra step in the red of changing those bounds. And then once we change those bounds, then we're just doing a normal definite integral where we just evaluate at the endpoints like we always do, but this time just in terms of u. So we'll go ahead and leave that there as a lecture, and that'll be it.